Ladies and gentlemen, it's with great regret that I cannot provide in this forum a more fulsome lecture on monads. Monads are a technology that is coming to that has long been talked about within the functional language community, but now you're seeing it surge to the forefront in software engineering interest more generally for many needs, including use in data science and in the context of creating scalable programs. And there's many motivations for the use of aspects. One of them is to achieve modularity via this sort of pattern we've seen before in this class of pipe and filter. Ways of sort of processing large amounts of data, large amounts of information, using a modular series of steps, each step having a well-defined job, and often doing so in a way that's memory conserving, that doesn't use unnecessary memory, so it performs the actions incrementally instead of going from a whole collection to a whole collection to a whole collection of millions of items each. It processes each item in turn for the full pipeline. These types of patterns, these types of pipe and filters are good for transparency. It's pretty clear what each of the steps are, for conciseness, for modifiability. You can insert a new step, take it out, and yes, for modularity. And so, we might have a population, and we filter those who are infective, and then we group by, this is actually Java 8 here, we group people by age, and we count the number in each age group. Okay, so that's an example of a sort of pipe and filter within the context of Java 8. And I say val there, but that's definitely Java 8. So this is bogus. It says it should not be val. It should be a declaration. Okay, a challenge here that we've talked about before in this class is nonlinear flow of control. We can have exceptions, special cases like nulls, and asynchronous operations. And earlier, I introduced in kind of an ad hoc fashion several types of monads. Can anyone remind us of a couple monads that related to these issues? They handled cases where there was missing data. They handled cases where there was a failed attempt to do something. And they handled things where there was work to be done, but it wasn't guaranteed to be done yet. Can anyone list those items? Option for the data maybe, so it may be that we have an answer or nothing at all. We have a value or nothing at all. What's another one? Try. So try could wrap up success or failure, right? We have a success or we have a failure. It's a value. And it's a monadic value. What's that other thing for asynchronous operations?
Futures?
A future, yeah. Now, it turns out that option and futures, I don't think try, but option and futures each have a place not only in Scala, but in Java 8, and they're actually represented in other languages as well. Haskell had maybe, as maybe. Did you cover that in 340?
Yes.
A little bit, okay. And this is a reflection of a general underlying class of things we call monads. And I'm not going to be able to do anything but give a very high-level sort of glimpse and comments on these. But I thought it was only fair because I really wanted to put something on the final exam. I need to have a little bit, at least a little bit more coverage for it to be fair, right? Don't assume it's all on monads. It's not. Okay. So what is a monad? Some people talk about a monad being a box. It's like a value in a package. I think of it as kind of a value or one or more values in a container. Okay. And it's a type of sorts. And it has information in it about values, but also some metadata. And it provides a way of chaining together sequences of steps, okay? It provides a means of sort of saying, okay, put this value in it, and then what does it mean to perform one step after the other in turn with this monad? And those steps, think about a step with option, where we're adding together successive values of these options, or filtering them, or what have you. We're performing one action after the other, and not only is the value inside the option, being calculated, becoming 5 and becoming 25 and becoming 300, but there's extra information being brought along as well. Is the value even there or not? Or is it nothing at all? And the analogy that's sometimes given, and I'm rather fond of it, is that basically these are programmable semicolons. So imagine if the semicolons that you have long suffered in languages like Java, you could actually tell them to calculate along additional information beyond the values being computed. Each of those values, you had to carry along some extra information. Maybe it's where that value originated in the program, what line number it originated on, when it was calculated last, or what have you. Monads allow us to carry around this extra information about the underlying values, okay? And it turns out by using them in the right way, we can really simplify computations, and we can make those computations much cleaner. So the way the monads typically work, they have a representation that is kind of a package or a container around your normal value. And this package can contain extra information and extra tasks that it allows, okay? So we might have something here that, for example, says this is empty. It's an option monad that has nothing in it. None, right, in the Scala context. Or this might be a string, and it says where that string got created within the program. Or it might be a value that says, is it computed yet or not? If it's not computed yet, it's not there, but we know how to compute it. With a stream, we might not have the value yet, but we know what? What do we know with a stream? We know I'm not sure I heard that properly, but we know basically how we're going to compute it when we need it. Right? Remember, it's lazy? Remember that? So we can give it rules to compute it when we need it, and once we compute it, it's cached. Remember the difference between call by need and call by name? Call by need, we'll call it, compute it, and when we need it, and often it will cache that value as well. Okay, it'll save it away. If it's not cached, we know how to compute it. So here are some monads: option, try. There's an either monad, or either left or right. Okay, where right is often the kind of correct value, and left is us lefties are being maligned here a little bit, but left is the less good value. It's the gauche value. Okay, and future is another monad. Okay, these are all monads within Scala, and Java 8 has a similar set. So optional, stream, computable future, and there's a whole set of other ones that are provided by third-party libraries. So common uses of monads here are to maintain metadata concerning the values. Like, do we have a value or not? Is this computed or not? Where did it originate within the program? How to compute it? To keep track and handle exceptional values through normal return mechanisms, like with empty values. Maintain contextual information, and to perform extra operations when we need to perform the next step. It performs extra operations. It can undertake extra actions like undertaking a computation if it hasn't been performed yet, or what have you. you may think this sounds awfully abstract. It turns out that these mechanisms are extremely useful. In a framework like Spark, which is the sort of most competitive data science framework out there, the use of monads allows you to keep around a memory of how these values got calculated. So if they have to be thrown out of memory, because you need to save memory, you can recompute them. You can recalculate them if you need to. Being a functional framework, it allows you to recalculate them and get the same types of values. We could throw them away without worries. Might keep track of where it lives, for example, on a cluster, etc. So why monads? Well, they allow for convenient composition of functions in a modular way while maintaining extra information, and fundamentally allows clean and concise handling of things that otherwise would cause exceptions and force a lot of ugly code around things. So it can simplify and clean up code. And it can allow for really clear expression of things. So let me talk about some of the things that define a monad, okay? Basically, there's a couple. I could provide a formal introduction to monads. We don't have time to do this now. But basically, it's a container. It's a value in a container, in a package. It's a value inside a package, and that package maintains extra information beyond the value that's in it. Okay? And basically, this package has to support two types of things. First of all, you have to be able to put a value into it. And this is called, in various subcommunities, pure, or unit, or return. In Scala, we use sum. So look, if I say sum of three, SOME here, let's go over here to Scala, and if I were to say sum of 3, I get back something that's a what? What is this sum? It's a type of option. Okay, this is a type of option. This is actually a subtype of option, and that sum basically took a value and it turned it into a wrapped value, a value that keeps track, is there actually a value there? Alternatively, I could do try, right? And unfortunately, this one might not be, yes, import Scala dot, what is it, util dot try. Okay. Okay, so here I have inserted a value into a try. What I get out is a try, right? This is the container now which contains this value, right? But I could do something of another sort, so I could try 3 divided by 0. And here I have a failure try. It wraps up this exception. Inside of it is what? Is it a value? Nay, it's an exception. It's an exception in there, okay? So these are examples of creating something out of a value, and I'll go back here. So we're taking a value, a regular old value, and we're putting it inside one of these wrapped values. It's M of A. It's a type parameterized monad, M, cap M, okay? So we're injecting a normal value into this. In Java 8, we say, for example, optional integer, where these less than and greater than things indicate the generic inside of it of some value, okay? Incidentally, just a neuron fired, and I realized I need to say something I should have said earlier. For the assignment where you're being asked to use Java 8 for that final component with functions, what you're being asked to do is just be sure that you use, you can do other things in Java 8, but the one I want to see, the one on which the marks will hinge, is you need to indicate using Java 8 functions or operators, the ways of encoding a function in Java 8 using a lambda expression to express it, and then encoding the type of it using a function. I gave a lecture on that several lectures ago, Java 8 functions, and you'll want to look at that. And when you take in something that would be a closure, would be a function in Scala, you'll do something similar in Java 8. You'll take in a function, but you'll need to use this sort of notation of generics, right? So this is how I create, using generics, optional value here. That creates a monad. It creates one of these wrapped values from something that's not a monad, from one of these raw values. So that's one operation that monads have to support. There's another operation too, which goes by the frequent name bind, but we call it flat map. Flat map. Flat map is not just a weird variant of map. In some ways, it's more fundamental than map. Remember map? Do you remember map? How could you forget? Perhaps you love map. Perhaps you hate map. Perhaps you are indifferent to it. But, you know, I could do map of this thing times 3, right? Here we go. Here's map. What was the difference between map and flat map?
Flat map went inside some structures and put them all up into the base.
Okay, good. So one prosaic use of flat map that we first saw was something like this, and it's a little bit distracting and made it almost seem like flat map was a hack. Okay, so let's suppose in map I were to take an A in here. I take in an A and I create an array of, for each element in here, I create an array of A minus 1, A, and A plus 1, right? Then I get back something. Why is it that I get this back if I did this? Why is it that I got that back?
You gave it a lambda and it operated on that.
Yeah, and so each thing, I mapped each element, which was an integer, into a what? Into an array. And so now we have arrays and arrays. And I think our first encounter with flat map made it seem like a hack in a way, because we said instead of doing that, what do we want to do? We want to do a flat map. And now we get out a flat array like that. We don't want to see none of those stinking arrays and arrays. We want to see all the elements. I'll put it out for a comparison here. All these elements have been sort of listed out one by one, right? So that's how we first used flat map. And it made it seem like it was a bit of a hack. But it's not, ladies and gentlemen. It turns out it's more profound than map, and it turns out it's more powerful than map. So ladies and gentlemen, what does flat map do? What's the difference between what flat map takes in a monadic context and what map takes in a monadic context? Well, in the context of monads, we're typically dealing with a situation where map, well, here, the distinguishing thing, I should say, I don't want to get distracted by map, is that flat map or bind is going to basically take a monad and then take a function that maps each element of the monad into a what? Into another monad, okay? And having done that, we're going to get back a monad. Okay, so here we are going to be performing an operation that takes in a function mapping the element inside this monad into its own monad, and we get back a monad. So this is ultimately, it's mapping through this function given to it, it's mapping a monad to a monad. Monad in, monad out. And we actually saw this with try for a moment, we saw it in a glimpse, where we had a try, which could have a value that either is good or bad. It's either success or failure. And then we have a function using that value that could itself fail, and therefore needs to map an operation, a value to a monad. The operation could itself fail, and as a result, because that operation could fail, we get back a thing that itself indicates, possible success or failure. So let's try this. Let's go over here in Scala, and here we are. Scala command line, val x is try, and I'm going to say try of 0. Okay, and now I'm going to say, okay, suppose I do here x dot map, and I say 10 divided by this value. What do you think will happen? Okay, yeah, okay. Here I actually want to get out a try, something that itself returns a try here. And actually, in this case, Scala hands it for me. Another way I could have written this, alternatively, would be flat map of try of this thing. Okay. Mumble. Okay. So this is a, and it goes to this divided by a. There we go. Okay. So another way I could have written it is like this. Do you see what I've done here? I have this monad, this try, x, and I perform a flat map with something that can itself fail. Do you see that? This try is indicating something can fail, hence it's wrapping a try. But what I get out is a what? As a result, what do I get out of this flat map? I get out a try. I get out a try, right? I get out the result of this operation, which is a try. Now, if I had done that with map, what would have happened? If I had done this with map, what would happen? What would I get out? I get a try of a try. It's really trying. Well, but no, it's a try. But with flat map, this is something now where basically I've specified, I have something which could have failed already, and then I specify an operation which could itself fail, even if it didn't fail already, and I get out a monad from that, which could indicate trying or failure. So I have taken this thing through a step which could itself fail, and I get out another monad from that. So this has been a step which I performed, and colloquially I might say I had A and I took 10 divided by A, but meanwhile I've been passing around along with that value. It's in a package, and this package says whether or not it succeeded, and here I performed 10 over A with the understanding that it's being operated on in the context of this package, the whole monad, not just the value. So bind basically takes in a monad, x, takes in a function, x here, that this thing that maps x to, maps the thing in the monad to a monad, and I get back a monad. I get back a try. I get back a try. Not a try in a try, which we would have had with map, but a try. So this is basically what allows us to compose these functions. We have these functions which themselves produce these monads, which can encode this additional information, like where a value originated, like whether a value is there at all or not, whether it succeeded, how to perform the next step of the operation, or what have you. And basically undertakes this function with the value and gets back a wrapped value. Okay? So here, this value that we get back, just like the value we started with, is ready for the next operation. It basically has gone through this step as encoded by the function, and now it's ready for the next step. And it can be applied to the next step, and the next step, and the next step. For example, we could have successive operations, any of which could fail, but they map from one to the next of these tries, and it's carrying around all along this information about whether or not it succeeded all along. So in Scala and Java 8, we use flat map to perform bind. It's called bind. Okay, so with something like optional, that first operation we talked about, pure unit or return, is just like doing this in Java, or a sum in Scala. And bind here is just with flat map of a function, just like we've performed. Computable future in Java, or Scala future. Here we have unit, where we can basically say, supply a sync, or we can just create a future of a value in Scala. This is Java, but with Scala we can just create a future. Bind, on the other hand, we can do in a number of different ways. One thing is with flat map, or with futures. We can do something like then compose with a successive operation. Okay. So one example that we could perform very nicely with monads that I haven't talked about is logging. The information that we're taking along is information about the log messages being produced, for example. So here we're performing a computation on some underlying values, but we're also keeping track of what has been logged. Or maybe the information is the output that's been made from the program. Maybe the operation is where certain values have originated in the program, where this was allocated within the program. We can do so with random number generation. And if there's a great, although very challenging book, Functional Programming in Scala, which has a very thoughtful, longer example on random number generation in Scala. And here we are not only keeping track of the number that's been generated, but what else do you think you'd need to keep track of? The seed associated with it to generate the next number. Okay? And we can carry that along with the value, this information about the seed in the background. Just like we can carry around this information about the try here in the background. Okay? It's carried along in a kind of in a way that in some cases can be almost hidden. Okay. Another thing would be you're dealing with coordinate systems, and you want to carry around a vector, but also the coordinate system in which it was generated. When you combine it with another vector, you use that information about the coordinate system associated with it, or you keep track of where something originated, when it originated, which user originated this value, and you carry around the value, yes, but also where it came from. That can all be part of the package that contains this value that's being carried around. And I don't have time to go into it, but we can broadly distinguish types of monads. And suffice it to say that there are certain monads that are actually themselves, the package is itself a function. Okay. I think I will leave it because I have one more task to do before my class is out, before my semester is out. I'm going to leave it here. But monads provide us, ladies and gentlemen, a way of wrapping values into packages and keeping the information about those values, the metadata about the values. Is it there or not? Is it computed yet or not? How do we compute it? Where did it originate? What coordinate system is it in? What log messages have been performed? They allow you to keep it in addition to the value. And then you can perform long sequences of operations as if they are operating on values when they're secretly operating on monads. And if you look at Haskell or you look at Scala, I am pained to say that I can't show you in this lecture the beauty with which you can write code that is secretly operating on try values or option values or computable futures, but it looks like it's just operating on numbers. Just looks like it's operating on the values inside of them, but secretly it's operating on the metadata as well. It's performing the metadata. It's like there are these computable semicolons keeping track of this other information. And the way in which we do this in Haskell is, I believe it's the do construct. In Scala, it's the for construct. So we can write for statements, and we actually saw that earlier. I don't know if you remember in this class, we used for to read in values and to process them. And basically, you're writing the code as if it's working just on the underlying values within the monad, but it's actually performing all the operations with the whole monad, keeping track of these things, and handling all the errors, of course, along the way with try, etc. It's a beautiful thing. And I will provide a link to a lecture if you want to see it, witness it yourself. But time is limited for us now. And we have 10 minutes, ladies and gentlemen. 10 minutes to wrap up this semester. 10 minutes to end the horror. Okay? Okay, so I'll move on with considerable regret for monads to separate topics. But I will provide a video in case you'd like to partake of them in greater detail in a way that will not be in any way tested on the final exam, but may expose you to a higher level of reasoning about them. Okay, so I'm going to stop my monads here.